There are several methods for calculating probability. Today we're going to deal with probability and compound events. In other words, more than one thing happening or more than one event occurring. And we've got two types of events we're going to talk about: an independent event where the second event, or even the event after the first event, is not affected by the first event, and a dependent event where the event after the first event is affected by that first event. If I have independent events going on, I just simply take and multiply the two probabilities together. If the second event is dependent upon what happens in the first event, it's likely that the chances of something happening second are less than the chances of something happening first. So if we're going to calculate that probability, we take the probability of the first event and multiply that by the probability of the second event happening based on the results of the first event. And we would write it this way right here if we were to write it in mathematical terms. So let's calculate a couple of these probabilities. So now we've got a survey where 7 out of 10 shoppers don't use coupons and 3 out of 8 only buy items on sale. Now this is a problem where you're going to have to read carefully. It says if the using coupons and only buying on sale are independent, we want to find the probability that the shopper uses coupons and only buys items on sale. Now, initially, we were given a number relating to the shoppers that don't use coupons. So we've got to use the numbers that do use coupons on this. So here's our first event that's happening, and here's our second event that's happening. Therefore, the first event has a 3 out of 10 probability. The second event has a 3 out of 8 probability, which gives us a 9 out of 80 probability. Problem done. Now in the second case, we find a guy with a bunch of different marbles. He's got 13 total marbles split up into red, green, and white. And he's going to reach in and pick 3 items from the bag. And we want to know, is it dependent or independent, right? And in this case, what he picks at a specific time, right, is going to reduce the chances of picking something the second and third time, if you will, right? But the order in which you pick it may affect the probability, but not the type of marble that comes out, because we aren't classifying something as like first, second, or third. They don't get places. So in this case, this is almost like a combination problem. We want to find the probability that everything's green. So we're again doing kind of like a choose situation or a grouping. So we want everything to be green. We're going to ensure that I have green marbles. So I'm taking from the greens and I'm choosing 3 of them. And that's going to go over the total number of ways to choose 3 marbles. Now within here, there is a individual probability calculated, but it's kind of tough to see each of those picks going on. Next example we're going to look at is something called a mutually exclusive event. And in mutually exclusive events, we talk about impossibilities for 2 things to happen at once. So if I said I want the probability of A and B happening at the same time, that would never happen, so that probability is 0. So the probability of A or B happening, or is kind of like the key word when we talk mutually exclusive. You take and add the 2 probabilities together. So we're looking for the key word of or. And tends to deal with a multiplication, or tends to deal with an addition. Now, if they're not mutually exclusive, we call them inclusive, not mutually exclusive, in which case there's some kind of overlap going on. And we'll give you a more defined idea of what this is, where it's a little touchy-feely right now. So what happens in this case is we have a situation where two things are happening at once, but there's some overlap going on. And what we want to do is we want to take and calculate it like a mutually exclusive event, add the two probabilities up. But if there's an overlap, typically you've counted something twice, and I'll show you again in a more practical problem. And you have to take out anything you've counted more than once. So that's why we're subtracting the probability of A and B on this. Let's do some problems. So in this case, Joe's got a total of 6 dimes, 4 pennies, or sorry, 6 dimes, 6 nickels, 4 pennies, 3 dimes. And he's going to take one coin out, and we want to find the probability of that coin is either a penny or a nickel. Now, when he pulls that coin out, it can't be a penny and a nickel at the same time, so we call these mutually exclusive. So again, if this is exclusive and this is an OR, we're going to take and add the two probabilities. So we want the probability of the penny, and we're going to add that to the probability of the nickel. Okay, the probability of the penny happening in this case is 4 out of a total of 13, and the probability of the nickel happening is 6 out of 13. Just add those up and we get 10 out of 13. And again, that develops because of the OR situation. Next example. So we've got a standard deck of 52 cards, and we want the probability that it's a face card or a red card. Now in this case, face cards can also be red, so we have an overlap. So let's do what we call a Venn diagram, and you might have used these anywhere between 6th and 8th grade somewhere. Talking about two things. Talking about face cards, and we're talking about red cards. All right. Now, in this case, we have a situation where there are a total number of 12 face cards. And if there are 12 face cards, we have king, queen, jack, over and over again. So let's do this. Let's say we'll call these, there's 2 kings in black, there's 2 queens in black, there's 2 jacks in black. And then we also have some red guys. 2 of those, 2 queens, and 2 jacks. But those are red cards. So notice I have those reds being both within the red circle and the face card circle. So we have an overlap here. So if I want the probability of pulling out a face card, I have basically, like I said before, 12 out of 52 chances of doing that. Now, the total number of red cards, I mean, if you keep that in mind, we've got double aces. I'm going to call aces ones, if you will. All right. So if we call aces ones, I'm going to find my red. I'll call them ace. What the heck? I got 2 aces, 2 twos, 2 threes, 2 fours, 2 fives, 2 sixes, 2 sevens, 2 eights, 2 nines, and 2 tens. So if I add all those red cards up in there, I get a total of 26. So that gives me 26 over 52 chances for red cards. This is red, and this is face cards. But I have an overlap of 6 of these. So really what I've done is I've counted these 6 twice, both in the red and in the face card. So what I have to do is I have to take out that overlap of face and red. So I'm going to take out 6 of those, which means I'll now only count them once, and this will get me my final probability. So it ends up as 32 over 52, which you can reduce. 4 goes into that. Let's go 16, 26, yeah, 4 goes in 8 times here, and 13 times here. So I get an 8/13 probability of that happening. So that was not mutually exclusive, it was inclusive. So here's another problem that talks about some inclusivity or non-exclusive events. And you have to read a little carefully, so I'll let you do that. And we have a group of hospital patients. Some have high blood pressure, some have arterial sclerosis, and some have both. So that's the overlap, if you will. All right. We find out that the high blood pressure patients who only have high blood pressure are 3/8. So I'll call this high pressure. All right. So they have a 3/8 probability. And I have high blood pressure or arterial sclerosis. That could be an answer, if you will. Here's my OR answer, and that's 13 over 24. Now, I need the probability of just arterial sclerosis. So, in this case, I'm going to call this AS. And this is what I don't have, the probability of just arterial sclerosis. But I have the combination of both. I have the AND part, which I would normally take away as the overlap. So that's a quarter. And then I can just go ahead and solve this problem. And in doing so, we get a total of 5/12. And that's the probability of anybody having AS. Moving forward. Again, this is a problem we've kind of dealt with before, but we have a word in the problem that's going to change the way we calculate it. So we've got 4 boys, 5 girls on a team. We need a subcommittee or a panel of 5. Needs to be chosen for the next debate, and we want to make sure we have at least 3 girls on the panel. All right. Now in this case, since we're talking about a subcommittee, this is like a grouping problem once again. So if I wanted to have exactly 3 girls on the panel and find that probability, I'd take from just the girls, which are 5 total, and I'd choose 3 of them. Now, which means that since there's going to be 5 total, from the boys, I'd have to choose 2 of them. All over 9, and I'm picking 5, 5. This gets me 3 girls. Whoops. But I don't want just 3 girls. I want at least 3 girls, which means I could have 3 girls, 4 girls, or 5 girls. And notice those words "or" came in. So I would have to add all these probabilities together. So in this case, if I wanted 4 girls, I'd take from those 5 and pull 4 out. And then from those 4, I'd have to pick 1. That's over 9C5 because I'm choosing 5 people. And then for the 5 girls, I'd have to take from those 5, choose 5, and from those 4, choose 0 over 9C5. And if I add all those up, I get my probability. So there are some problems for you to answer. Do your best at them. We'll take a look at them tomorrow and go from there.